Okay, so welcome to the next episode of the Industrial Technology Multimedia Revision Series. So last time we talked about text, fonts, pagination, all that sort of stuff. And today we're going to move on to the second section of the syllabus, still on page 43 if you're following along, and this is about graphics. So graphics are images, okay? So even though text is technically an image, graphics, when we're talking about it, are mainly like pictures, images. They can be both moving or static, but when they're moving, for the purposes of this syllabus, we call them videos, okay? So graphics, when you're thinking about it, let's keep it to still images, pictures, things that you find on the internet, JPEGs, vectors, all that sort of stuff. So the first thing that you've got to get your head around is there's two main classes of images. There's bitmap or raster, and there's vector. Now, the two differences between those, bitmaps or raster images are created by pixels in a grid. So they're little dots of color and hexadecimal values of code, which are represented on the screen as a color, dot, 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 next to each other. They're really, really tiny. So when we zoom out, our eyes get confused and we see those distinct squares and dots of color as shades. So this is really good for a number of reasons. The first reason is that it is really easy to imitate life and the colors of life with those little dots. We just subtly vary the code that is represented by those dots, and we can have one shade of, let's say, the pink in my face next to another shade of pink in my face just by changing those values, and we can do it like hundreds of times per centimeter or inch of the screen, and that will create that tonal variation that we want. Why are bitmaps or raster images bad? Because if you scale up those little dots of color, those squares just become larger in size, and then you get pixelation. Now we'll go into that in more detail later. The other type of images are vectors. So vectors are mathematical points, and then we choose the angle of a line that goes between those mathematical points. So kind of like a dot-to-dot image, if instead of going by straight lines, you could say any sort of degree of curve between the two. So you've got point A, point B, it could be a straight line in between those, could be a curved line in between those. It can't be sort of a straight triangle point though, because if you had a straight triangle point, you would need a third dot there. So you'd have like dot, 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 straight line, but you could also do a curve in between that and make a circle, a semicircle shape, that sort of thing. Okay, so why is this good? Okay, so say you had a straight line here, or let's do that semicircle later again. All that you need to do to make those bigger is move those dots apart. So this one moves obviously up at the same time. You've got that same curve line going through it. There's no pixelation there. So you can take a logo that's made as a vector in a program like Adobe Illustrator, or I'm just going to say Illustrator, and you could make it the size of a bus. No problem, no pixelation. You take a Photoshop logo that you've made that was designed to sit on the front of an A4 piece of paper, try and make it the size of a bus, and it's going to be really pixelated. So it's going to look horrible, it's going to look unprofessional. And you see that with a lot of low quality signs. Sometimes people don't really care about that sort of thing, and now that you've learnt about it, it's going to irritate you. But a lot of people don't seem to care. It irritates me. Anyway. So bitmap or raster images are pixel based. Now this can be sometimes a little bit confusing because there is a file type called bitmaps. Now a bitmap is a bitmap image, but a JPEG is also a bitmap image. So you need to understand that bitmap is the overarching way for how these images are made up, but it can also be a file type. So I like to call them raster images or pixel based images just to not confuse myself. But pixels are squares of individual color. We've talked about this. They make up everything that you see on screen. Everything on screen is basically a pixel image, even if it's a vector image. It's still represented by pixels on screen, so it has to be a pixel-based image, which is confusing, okay? But Computer monitors display these pixels, and the number of pixels on screen depends on the resolution of your monitor. The higher resolution you monitor, the more pixels that are in a dot of color. Bitmap images are resolution dependent. So if you've looked at something on your computer screen at screen resolution, most screen and web resolution is 72 pixels per inch. We can call that 72 DPI for, I think it's DOS per inch, or PPI, which is pixels per inch. It's interchangeable. But when you print something out, it prints out at 300 PPI or DPI. So when you scan an image in, you use a desktop scanner or a photocopier or something, and you scan it in at 300 DPI, it will be larger when it's represented on screen than in real life, because what the computer is doing is it's representing it at, well, it's downsampling it sometimes, which is making it a little bit larger on screen. So when we resize our images, we need to be careful that we don't sacrifice our image quality if we care about image quality. I mean, you can't always just resize something huge. It's going to look bad, but if you don't care, problem solved. But what we want to do is we really want to sort of work with our resolutions to understand when something's going to pixelate. So if you've got like a little square, like let's say we have an image that's 5 squares and it's really tiny. If we want to stretch it up to A4 size, those squares are just going to get bigger. So it's going to become blocky. It's going to look a little bit like Minecraft or something. Let's hope that reference doesn't get completely outdated. Scaling an image doesn't affect it permanently, okay? You can bring that image back down to the original size and it will get rid of that pixelation because it's taken those larger squares and it's just pushing them back down again. So, you know, look, if you really want your images to look good, make sure you take them at high quality, okay? So if you take a picture with your camera or your phone, make sure you understand that there are limitations to how big you can make that picture. If you're taking it with a good digital camera, you can kind of change the size of the image that's being taken, so you could shoot in RAW, and that's going to give you a higher quality image. Let's talk about the different types, common types anyway, of bitmap raster images. So you've got a GIF, some people call it a GIF, you've got JPEG, Joint Photographic Exports Group, PNGs, which are basically GIFs, but better these days. They've added a lot of stuff to it, so a GIF was controlled by one company. PNGs are an open source version of that. You've got a TIFF, you've got a PSD file, and then a BMP. So you can convert between them pretty easily. All you need to do is open the file and hit like save as. So if you open up any of these files in Photoshop, save it as a different version and then output it, it'll work pretty well. There are benefits to all of these different files. So for example, PSDs can have different layers in them, so it's not just a squished image. JPEGs are usually pretty compressed, so they can be small in size while still showing a lot of visual data, so lots of different shading and stuff. GIFs can be animated on the internet. PNGs don't really have too much compressing, and they can also show transparency, which can be really good. So an example of that would be if you had a background that you wanted to be clear because you wanted to put the picture on top of another picture later, a PNG will allow you to do that, whereas a JPEG, if you were to save that out, would just create its own white background, which is just a mess. So if you're using, say, After Effects for animating something and you export your images from Photoshop to PNGs, you can put them on whatever background you want later, and that can work really well. JPEGs are just a mess with that sort of thing. But a PSD will also save transparency information, but it's much larger in size. Let's move on to, we've talked about those. So let's talk about resolution. So resolution is the amount of information basically that exists in your image. I'm going to talk about vectors first, because I've talked all about these bitmaps, and resolution matters to bitmaps, but let's talk about vectors. Okay, So vectors are to do with mathematical points. We've talked about this before. So they scale in between those different points. We can scale them up, we can scale them down, we can do all of those sorts of things, okay? They're independent of resolution, basically. You can decrease the size, you can increase the size. Most fonts, except for those SVG fonts that we talked about the other day, are vector images. They're not also rectangular in shape. So a bitmap image is by necessity made up of those blocks of color. So you are restricted to a blocky shape when you really get down to the very small size of it. Most PSD or GIF or any of those files will save out as a square or rectangular file no matter what detail is put into them. Now a vector image can be whatever shape you want. It can be like moon shape, it doesn't even matter, alright? That's the great thing about it. I like vector images, but they definitely have caveats with them. So for example, you can't produce photorealistic images with vectors, you just can't. Now we've gotten pretty close with some of the Illustrator image trace high fidelity photos, and that will create sort of hundreds of little vectors that sit on top of each other, but it just it'll always look kind of blocky and posterized and without detail. And there's not really anything you can do about that. And the reason for that is because vectors are those mathematical points which creates a stroke around the shape, and then there's a fill in that shape. Now that fill is either one color value or a gradient, but you can't sort of do independent fills and shading across that vector. So it just won't give you that sort of photorealistic appearance with a vector. It'll have a cartoon-like appearance. Now that can be cool if that's what you want, but they're becoming more advanced in time. So we can do a lot more stuff with vectors than we could a decade ago. You can actually add bitmapped textures on top of vectors. You can create blends and shading, and we're growing. So we're getting to the point where we can almost get an approximation of a bitmapped image that can be scalable, but we're never going to get, well, at this point I don't see us getting there with that sort of best of both worlds things. You can also rasterize an image. So remember we talked about raster files being pixel-based, so you can take a vector image into a raster program and rasterize it, and what that's going to do is it's going to take the current values of that image and then change it into pixels. What are the advantages of that? You can then add shading and all those sorts of things to it. What are the disadvantages of that? Well, it's now a pixel-based image, it's not a vector image anymore, so it is resolution dependent again, and you've got all those scaling issues that we talked about before. Okay, so that's vector images. So common vector formats, we've got Adobe Illustrator files, so AIs, you've got SVGs, which is a scalable vector graphic. So that's when we were talking about those fonts, SVG fonts. They are vectors, but they've got a whole lot more detail in them. Yeah, really, SVGs are the main ones. Adobe Illustrator, there's DXF, which is some cutting files for AutoCAD. That's what you would use in, well, at least in our laser cutter, you use DXF files. The most popular vector drawing programs are Adobe Illustrator, CorelDRAW, which I've never used. There's a few other ones, but really Adobe Illustrator is the king of vector art drawing programs, but you can use vectors also in things like SketchUp, and yeah, that sort of thing, okay? There's also a thing called metafiles. So metafiles include both vector images and raster images. So the object is still a vector, but the fill of that vector stroke can be a bitmap. So common ones of those, you've got EPS files, you've got PDF files as well. So a PDF image file can be a vector and it's got the fill in. Okay, so in your textbook you've got some examples of pixel-based and vector-based ones. That's on page 14 of the current 2018 Term 4 textbook. But the most common ones for raster image files, BMPs, GIFs, JPEGs, PNGs. Vector-based, you've got AI, CDR, CorelDRAW, SWIFT, or Flash files. That's a vector. and it goes through a bunch with some information about it. But if you know a couple of file types, so if you know, let's say, JPEGs, bitmaps, TIFFs, PSDs for the bitmap raster, and if you know sort of, let's see, if we can use DXF files, AI files, and let's say Swift files for the vector ones, you will do okay in the HSC. The only thing you'll ever really be asked about is, you might get asked which of these are bitmap-based image files, and they'll give you 4 files. You've got A, B, C, D, and they'll create all those types of files. They're going to stick to the simple ones, all right? You're going to get your JPEG, BMP, TIFF, and then they'll chuck in like SVG. So that's wrong. Process of elimination, all right? That's really all they're going to ask you about, although it might give you a short answer question that's like, what kind of file is appropriate for this sort of thing? And then you can say, a bitmap-based file such as a JPEG would be good for this because the file needs to be small to go on the internet. You'll do it. You'll be fine. So we now need to talk about resolution and color depth and all of that sort of stuff. So this sort of stuff can just get a little bit confusing, but this will be the last thing that we talk about today. Okay, so we are going to talk first about compression in images. So why do we use compression in images? We use compression in images to make images smaller. We use compression in anything to compress it to make it smaller. So if you overly compress an image, it will get pixelated. So really, first off, let's talk about when we would use compression. There's no point really in compressing a vector-based image because it's resolution independent. It's the same size no matter how big or small it is. It's still got the same amount of data. It's still a relatively small file size because vectors are small by nature, because you've only got data for those points where they are and then the information of the lines in between them. So even if it was 10 stories tall, you still got the same amount of points, the same data between them, same file size. If you've got a bitmap image though, and it's the size of a skyscraper, you've got all of these individual pixels of color. Now, if you have a picture of my face that's the size of a skyscraper, there's just going to be a whole bunch of pink on here. You might have a meter where it's just the same shade of pink. So we could compress that. We can say, all right, so this pink color is very close to this pink color, so we're just going to say that it's the same, and we're going to give it the same information, and we're going to throw out all that extra data that says it's different. So that's effectively lossy compression, where we chuck out all that extra information. But we compress by throwing out information or by making the file size, so making an image smaller. When we make an image size smaller, those pixels get crushed together and the value of them gets averaged out. So we have this pink again next to this pink, we smush them together into one pixel, we look at the difference between them and we create an average in between, and that's the pink that is shown. Once we compress it down like that, we can't get it back, all right? You can't pull it out large again and then just average that data. It just will not work, okay? So if you make something smaller, you can't really get that image back. But remember, as I said before, if you stretch an image out and it gets pixelated, you haven't destroyed any data, you've just made that data bigger, so you can squish it back down and you'll be fine. If you compress and you throw your information out, you can never get it back. But that's if you use lossy compression. There is another type of compression. We'll talk about it in another video, okay? Don't worry about that for now. So JPEG compression, when we save a JPEG, so to make a file small to put on the internet, it looks at 8 by 8 pixels. So 8 by 8 pixels, so 64 pixels in total, a little square of the image. And it reduces the detail in each block. So it looks at those 64 pixels and it goes blue, if it was blue before. And then it picks a certain value for the blue and it compresses down to that size. The more compression we do, and the higher the compression ratio, the more simple the end result is. So you have those 64 blocks, you might say, all right, we've got a couple of different values of blue, you do a really compressed JPEG, it's just like one color. And the more that you do, the the more that you compress, the more noticeable and blocky the image is. You can usually get away with it if you've got pretty simple information. So I have an example of if you did the sky, it's really like mostly shades of the same blue on a nice day, so you can get away with compressing it a lot. But if you compressed a close-up picture of a bird where there's a whole lot of color variation, you'd notice it quite quickly. Alright, so let's move on from there and let's look at resolution. The higher your resolution of a file, the more image detail and the larger the file size, but that's only with the caveat without becoming blurry or grainy. So you can always make an image bigger. It's just going to go blurry or grainy if it's a bitmap image. So resolution is measured by how many pixels the image contains. So you've got height by width. That's what you work it out. It's a simple area calculation. And so 1 megapixel equals 1 million pixels. Okay? So a 10 megapixel camera from like the 2000s is capable of taking an image that has 10 million pixels. Okay? Does that make sense? Alright. The higher your resolution, the more pixels, the more information, the bigger your file size, while still keeping it looking good. But there's another thing, there's another equation in there, and that's color depth, or bit depth. So color depth or bit depth is pretty important when you're talking about the value of an image. So basically, we've already talked about how you've got so many by so many pixels in your resolution, and that's a very big component of the size of your image. But each pixel can also contain different amounts of data. So if you've got, for example, a 1-bit image, it's capable of showing 2 colors, either black or white, or red or white, or any 2 colors, off and on. So you get this black and white look to it. Okay? So we can only show 2 images in it, two colors in our image. So it's pretty low quality. But it's an exponential equation. If we've got 2 bits, we can show 4 colors. If we've got 4 bits, we can show 16 colors. If we've got 32-bit, we can do like 4 million colors. So the way that you work out the bit depth formula is you go 2 to the power of whatever your bit depth is. So if you've got 2 bits, it's 2 squared. If you've got 32 bits, it's 2 to the power of 32. That's how you work it out. So if you've got 4 million colors, you can show in your image 4 million different values of pixels. Now, why would you ever need 4 million different values of pixels? Well, let's go back to my face again. We got pink, right? If we just do my face as one type of pink, it's going to look ridiculous. I'm going to look like some kind of weird serial killer wearing a mask or something, someone else's face. We need that shade, we need that variation. Now, is there a need for 2 million different values of pink in there? Debatable. But if we have the data there and we want to do it, then we can. Now, you might think that adding in all of these pixels is just going to give us crazy high file sizes. But a 1-bit image might be 4 kilobytes in size. A 32-bit image might be 98 kilobytes in size. Now, it is substantially bigger, but 98 kilobytes is tiny, at least at this point in time. Now, if we're going over a slow internet connection, 98 kilobytes is still going to do pretty well with one single image. When we have a web page that's got 40 images on it, then we start to see problems. So the takeaway from this is the higher your bit depth, the better the value of your image. It's just going to look nicer, okay? The lower your bit depth, the more you're going to blend between your colors. There's going to be less detail, less shading, less vibrancy. The higher your bit depth, the broader the range of distinct colors and tones. So let's work out how to do file size. And I think that might be where we leave it for this lesson, because it's a pretty big idea, okay? So the file size of an image is the number of pixels times bit depth times the height by width. Okay, so that will give us the file size in bits. Now, we never get asked for the file size in bits. We always get asked for the file size in bytes. Now, there's 8 bits in a byte for an arbitrary reason. Half a byte is called a nibble, by the way. You might find that interesting. I certainly don't at this point. Okay, so 1 byte equals 8 bits. 1 kilobyte equals 1,024 bytes. 1 megabyte equals 1,048,576 bytes. 1 gigabyte equals 1,073,741,824 bytes. Okay, so the way that you can work that out is they're divisible by 1,024 of each other. Okay, so what you need to do first is you need to work out the number of pixels. Okay, so if you get a question and it asks, we've got an image that's 1080 by 720 pixels wide, all right? So the first thing that you do is you multiply those together, and then it gives you the area, the number of pixels within them, okay? Then you multiply that by the bit depth. So if it's a 2-bit image, you multiply it by 2. If it's an 8-bit image, 32 image, multiply it by that, okay? That gives you the amount in bits. You'll never get asked for the amount in bits in an HSC question, but if you do, you're done there. You just write down the amount of bits. You will get asked then, is it bits or bytes? So they might ask for it in megabytes, they might ask for it in gigabytes, they might ask for it in gigabits. Now, the most important thing that you need to understand from this is if they're asking in bits, it will have a lowercase b next to it. That's a D, a lowercase b. So megabits is MB, lowercase. Megabytes is M capital B. So always look for that capital or that lowercase. That's what you need to do to make sure it's working fine, okay? So it asks for it in bytes. Divide it by 8. Then you need to add in your modifiers to take it from bytes to megabytes or gigabytes to whatever it is. So we divide by 1,024 for each one of those. So if I have an image that it's asking for the amount of megabytes, first I get my number of pixels, multiply that together, width by height. Then I multiply that by the bit depth of my image, so the detail of each pixel. Then I've got it in bits. I divide by 8 to get it to bytes. I divide it by 1,024 to change it to megabytes, and I'm done. Okay, so that's our sizing. Now, it can be pretty confusing to work that out, but that's literally the math in this subject. Once you've worked out that equation, you're good to go. So I'm going to put that up behind me the entire time if I haven't already. It's not too hard once you get started. And it's all, you can carry it all on over to the, what's it called? You can carry it on to audio file size, you can carry it on to video file size as well. It all works the same. So at this point, I think we're into where we need to finish off today. This is already quite a long video, and I think at this point, you've kind of understood the difference between vectors and bitmaps. We've gone through a little bit of file sizing. We've done everything that we need to do in terms of that. So thanks for watching, and hopefully you found some value in today.